And so screen share, this always pops up. Okay, so what we did is that we finished two examples, and the here I'm giving you different examples so you can appreciate what you need to do with ADA in order for you to be able to do it properly and have the program do the analysis for you properly. Now I just want to hold on, annotate. Okay. Now here, guys, in reality, okay, in reality, when this thing would be built, in other words, if somebody would put up this beam and this would be the load, and these supports represent either columns, whatever it is, okay. In reality, this would be one continuous member. Okay, in other words, somebody like this is only what 22 feet long, so the guy would buy a 22-foot beam here, okay, and that's in reality how the member would come to the job site, and that's how it would get installed. But when you're analyzing the ADA, what they need to do is that for the beam to be able to interact with the reaction area here, in other words, the support. Now, this is a reaction area, this is support. This could be a column, this could be a bearing wall, whatever it is. Okay, ADA needs to create a node here, okay, so that the member can interact with the reaction area. And if, for example, if you put a node here and you put a node out here, right, and you draw a member from there to there, ADA won't know how to interact with this member. So a lot of people do this misconception, like they have a node here, they put a support, they put a node there, then all of a sudden when it comes to adding the member, they go and they add the member from that node all the way to that node. But there's no interaction here between the support and the member. So that is absolutely wrong, okay? So here, what's happening is that, like I said, when you're, before you rush to ADA, you should determine and say, okay, I'm going to need a node here. I should change color, make it red, a little bit more apparent. I'm going to need a node here. I'm going to need a node here so that the member can interact with the support. I'm going to need a node here so that the member can interact with the support, and I need a node here so I know where the member ends, okay? So basically, I will have 1, 2, 3, and 4 nodes. Now, guys, what I do so that I don't make a mistake, I don't rush to ADA right away. As a matter of fact, I do this. I take my sketch, I'm going to have a node 1, node 2, node 3, node 4. I do this on a piece of paper. And then here what I do is I say, well, this is my 0, 0 coordinate. This is my 4, 0 coordinate. And then all of a sudden, this is my 16, 0 coordinate, you understand? And this is my 18, 0 coordinate. So this way I don't have to do, like I already have that information, because all you're really doing with a software is you have to input. But so instead of doing this mentally in my head, I take out my little calculator, I make sure I got my coordinates. And then once I got my coordinates and everything else, okay. Now in this problem here, what I did is I gave you the geometry, okay. I gave you all the geometry and the load in imperial. But when it came to the member, I gave it to you in metric. So I just want to show you that with ADA, that's not a problem. You can have all your geometry in imperial and all and you can get all the information regarding the different shapes in metric, and that's where we're going to be going, okay? So now we're going to start here, and just like we did, this morning, first thing we're going to do is, of course, excuse me, okay? So like I said, what I like to do, I hope everybody started a new file. Okay, that's number 1. Is everybody right here at the very beginning of their file? Now, at this point here, like I said, what I like to do is I like to go to project configuration, go to preferences, okay? Now, this is where, for example, I choose that I'm going to have the shape in metric. So I'm going to have my radio button in metric, but as far as the geometry, I'm going to do it in imperial. So by doing that, I don't have to worry about it. Come back, oh, I forgot to change it. I'll do it right away. And this way, when I go look for my shape, the program will actually bring up all the metric shapes and not the imperial ones, okay? And then at the same time, like I said, these dialog boxes, okay? And even if you I used to do this at the very beginning anyways. And even if you do it, like I think there's some tutorials that they offer you by Cratech, and the first thing they tell you is remove the check marks in the dialog boxes. Oh, I don't know why the programmer even bothered doing that. He should have left them blank, and then if you wanted to do that, you should check them on if that's what you want to do, okay? So that's the first thing I want to do, is make sure I'm working with the right units here, okay? And of course, and avoid having these. I can leave these on. You can understand what I'm saying by you don't want these things to pop up on you. So for example, when you pick a member, it's going to tell you what's put the member anyway. So that's what you want to avoid. And you press OK. Now, I like to see on the screen what's being done by the program. So I like to go to my visual graphics, okay, or my visual options in this case. I'm thinking of visual graphics, I'm thinking of Rivet. And of course, I always like to see the lengths of my members. I like to see the material, I like to see the shape. So this way, once I place my nodes, the program is going to tell me how long the member is, and so on and so on. So, okay. And at the same time, I really don't like this, X and Y coordinate here. I know that this is X, I know that's Y, and I like to remove that so it doesn't clutter my screen. I apply, and it's gone, okay? So like I said, first thing we do is we determine number of nodes. I should have left that. So I go to structures, go to nodes. So I'll wait for you guys to hit the structures tab, pull down, you get the pull down menu for structures, go to nodes. And here we said we needed 1, 2, 3, 4. So I'm going to put 4 rows on my spreadsheet. And these are spreadsheets, believe it or not. This is an Excel spreadsheet. And now, the first one's going to be normal. In other words, right here, excuse me. Where's my, okay. This one's going to be a normal node. This one's going to be a support node. This one's going to be a support node. And this one's going to be a normal node. Okay, so that's, okay. And so this one's normal. The second one's going to be a support. The third one's going to be a support. And the last one's going to be a normal. Now, the first one I always like to leave the first one at 0, 0. Then the second one is at 4 feet. Okay. Third one is at 16 feet. And of course, the last one should be at 18 feet. So, and there I put in, and of course, since I'm not moving along the Y, we will, have things that will also be moving along the Y, but that's further down a couple of weeks from now. So far, so good. So I've created my nodes and I've created my supports. So I press OK, and that's what pops up on the screen. So I'm going to just zoom in. And like I said, once I've created my nodes and I've placed them according to the geometry that I have, before I move on to my members, I want to make sure that my nodes are properly modeled. And like I said, by default, this is fixed. There's a red dot there. There's a red dot there. There's a yellow line there. There's a yellow line there. So in other words, no displacement this way, no displacement this way, no rotation, no, okay. So this is completely fixed as opposed to having a pin and a roller. Now, if like I said, you can do it here. Like in other words, this is to pick a support, activate supports. I can pick it here. I can just pick that, and I can change it here if I want. And you can go back to your structures, you can go to supports, and you can do it here. Whichever you feel more comfortable doing, it's up to you. So for support number 2, it's fixed in the X, fixed in the Y, but it's free to rotate about the Z axis. So I'm going to change that to free. And as far as the second one, it's free to move along the X axis. It's not free to move up and down along the Y axis, but yet it's still free to rotate about the Z axis. In other words, I'm not limiting the rotation. And therefore, that's how I create a roller, or I model, I should say. That's how I model a roller with this program, okay? And I press OK, and I come back. I notice that the red dot is gone, so that means I freed the rotation. I notice I only have 2 yellow lines here. That means I'm restricting it along the X and the Y. That's what we're doing in terms of a pin. And here I'm only restricting along the Y, and therefore that's exactly a roller. I'm letting it translate as much as it wants, or display as much as it wants in the X axis. And this X here is your first node, your normal node, your support, and your other node. So once you've got your nodes, once you model support, then I move on to the next step. I worry about adding members. So you remember that you have to activate the members here on the side menu, activate the members. Now, once you've done that, you can add members. And as I said, remember the way when you add members, I'm not going to do it right now. Okay, so for example, when I add a member, if I go from here to here, you'll see somewhere in the program, they'll talk about the I and the J. I is where it initiates, the J is where it finishes. So since I started here, this would be my I node, that would be my J node. And therefore, all the information that the program is looking for, if I want to place a load at a certain position, I'd have to remember where I started and where I ended. And that's how the program is going to take the information and put it into the program. Then, of course, I got one from there to there, and that's 12 feet. And I got one there from there to there. So that's why I like the visual. So this way, I see I have 4 feet there, I have 12 feet there, I have 2 feet there. That means my nodes are correct. Now, if I happen to make a mistake, guys, if you happen to make, let me escape out of here, okay? So let's say I had made a mistake on placing this node here, okay, or that node. Well, you simply go back to your structures, you go to nodes, and you simply correct whatever you need to correct in the coordinates. And it's going to correct it. So you don't have to delete everything and start over. You can go back to the spreadsheets and you can do any corrections you want. If you forget to add a node, you can go back, add the node, and then you can give it the coordinates and so on and so on. So you just, this can be modified as many times as you want and can be corrected as many times as you want. So that's one thing that I like about this program. And now that I've got basically the geometry of what I want to model, what I need to do now is, of course, assign the members. And like I said, here this is metric. As soon as you see W310, this is like a 12-inch by, I think this is 12 by, I forgot what it is, 12 by 16. I'm trying to remember. Anyways, so now since they are all the same, so like I said, when you want to pick something with 88, you can draw a window. Okay. Or if you need to pick only 2 members, you pick one, you hold the control button down and you pick another one. If you don't hold the control button down, it won't keep adding to what you're picking. And then you hold the control button down, okay? So you can make a window or you can control and you can add. So in this case here, I picked all 3 members. I right click, I go to properties. And at properties, of course, this is where the properties are all stored in the program, right underneath here. So is everybody okay? Is this a little too fast or do you want me to, is everybody up to speed here? Are we good?
Yeah, all good.
All good, guys? Thank you, Emmanuel, thank you. Okay, so now I am going to, of course, click here and I love this program because you can do steel, concrete, timber. We won't be doing any timber this year, but we will do some concrete, we will do some steel, okay? Timber would be next year in the wood course. So I'm going to click on steel, and these are all the steel shapes that basically the industry uses to build steel structures, okay, HSSs and so on and so on. And therefore, I click there, and then of course I have a wide flange section. Therefore, this is all the wide flange sections are stored here. And of course, it goes from the biggest wide flange section, the W1100, which is, you know, it's over a meter high, all the way down to a W100, which is really, really small. And we have a W310. So I look for 310. Oh, there's 310. And of course, you're going to go down, and it goes by kilograms per meters. And of course, it starts with the highest kilograms per meter all the way down to the lightest one. And this one's is a 21, which happens to be the last one. Now, if at the beginning where you put the project configuration and the preferences, if you would not change the radial button, this would have been all in imperial. And since you guys aren't very familiar with the imperial ones to the metric ones, you wouldn't know what to do. So you might as well make sure that you're on the right properties for the section so that when you come to this part here, you'll be able to recognize which ones you're picking. Now, this is just that all these shapes are being produced here in Canada. Well, they're all being produced in the States, but they used to be produced both in Canada and the US, okay? Now, all these shapes are being produced in the US, no longer in Canada. And that's why they have these two. Now, they also have European shapes and so on. So you press OK. Now, so now you've assigned the shape of your beam. Then the next would be the material. So you fly out, and of course, you're talking about steel. Now, this is the Canadian steel, and since the, I'll probably throw some Canadian steel examples maybe next week or whatever. But in this case here, I say it's an ASTM A992, grade 50. So I go here and I look for ASTM A9950. And there you go. So you just double click on the material and it selects it. And if you want to include the dead load, make sure that you put dead load, okay? And that's it. So now you've assigned it, you press OK. And here you see you've got your shape, you got your material, you got your length. For this member here, you got your shape, you got your material, you got your length. Everything looks good. I'm happy. That's what I want. And this is my first part of my, let's say, analysis. I consider this to be the first part whereby I have finished modeling my structure. Now, once I finish modeling my structure, I like to move on to my loads. So I'm going to remove this from the screen so that it doesn't clutter the other information. I will remove the length, materials, and the shapes. Apply, okay. So now, before I can actually, okay, because I've activated the dead load on the members, it's already there, you see? I'm saving my project. Okay, and guys, believe it or not, that's the dead load. Oh, this is in pounds per foot, okay? Isn't that nice? And if I want to know what it was in kilograms per meter, I just have to change the units, you understand? Go back to and change the units. So this is the dead load of the beam in pounds per foot. And if I wanted to see what it looked like in kilonewtons, or like this should be, in theory, should be 21 kilograms per meter, you understand? So I go back to project configuration. At this point, I can go back and say, give me the, well, no, I'm going to leave it in feet, but I'll put it in metric right now, just so that you guys can see the difference. And there you go, 0.21 kilograms per meter. And that's, basically it. So that's pretty good. And sorry, let me go back and go back to, like I said, at any time you can come back here and put it back to Imperial for the, I'm going to go back to Imperial. Okay, so this way I can, now, I'm going to create load cases, okay? So therefore, I'm going to create load cases. So I'm going to go to load case, and I'm going to define my load cases. Now, it might seem that I always call this live, okay? But in reality, I would have, if we were doing a real project, I would have superimposed dead loads, I would have live loads, I might have snow loads, I might have wind loads, okay? So that's when I would have different types of loads. But for now, I will call everything live, so we don't have to. So I'm going to call this live, just to give it a name. And of course, you don't have to define it, but if it was a live load and you want the program to generate the load combinations, you might as well assign it as a live load. So that's okay. So now that I've done that, and make sure that the load, activate a load kit is on, because if this is not on, you won't be able to fly out the menu. Now I can go to live. So now I'm ready to assign loads. So what I'm going to do is, right now, the only way to assign a moment on ADA is add a node. Keep that in mind, guys. It's add a node. So therefore, I'm going to make sure I pick here activate node, first of all. Everybody make sure you pick activate node. So you activate the node, okay? And that has to be like a bluish. So does everybody, I'm going to wait for everybody to do that properly, okay? So if you pick a member and you add a moment, it's going to be putting moments all across the member. And that's one thing I don't like about this program. It's piss poor when it comes to adding moments as a load, okay? So you pick here, make sure that you're picking the node, and I double click, I pick that node. And of course, what's happening here now, just so that you guys understand the sign conventions for, okay? For example, when it's a vertical load, up is positive. For ADA, down is negative, okay? When it's a horizontal load, from right to left is positive. I'm sorry, from left to right is, and this is negative. For ADA is what you guys are so used to. If it's counterclockwise, it's positive. If it's clockwise, it's negative, okay? Right now, this is clockwise, and therefore ADA wants you to put a negative sign here. And of course, it's rotating about the Y, I'm sorry, the Z axis, and that's why you put the value here, okay? And if it was we'll be doing these later on. So that's where I would put the value. So I'm going to come here. Now, if you don't want to convert this into kips per foot, of course, you can always change the units and then change it to pound foot. Pound foot. So this way you don't have to, you can just change it to pound foot. And of course, here you would be putting minus 1200, and that's because it's rotating clockwise. Okay. So now, unfortunately with ADA, when you put moments, you don't see the value. All you're going to see is a red dot. That red dot means that you've applied a moment right at that point. And unfortunately, and here it tells you the magnitude, and for some reason, it doesn't tell me the value. Okay, it tells me the units that I applied it tells me where I applied it, but it doesn't give me the values. That's another quote unquote item about this program I'm not too crazy about. So, but it has other good benefits. So there, now I've applied that load already. Now the next one is going to be for the member. So since I'm going to be picking a member, make sure you activate the member, activate members. Okay. And then once I've activated member, I pick the member. Okay. And I can double click on it, and this is what comes up. Okay, so you either right click, get properties, or double click, and this is what comes up. And now here it's in pounds per foot, great. So that's all I need. I only need to apply one distributor load. And of course, this would be minus 800. And it's going to automatically put minus 800. It's assuming that it's going right across the member. Okay. So that's it for that one. There's nothing else that I want to add to that member. So that member has been completely loaded. Now this member here, double click on it. Now, if I want to start with the concentrator load, let's start with the concentrator load. No, it's 2,000 pounds. So I don't want to do the math. I'm lazy. I'm going to change the units, and I'm going to go to pounds. Oops, sorry, cancel. I want to change the units for, oh, sorry, here. I want to change the units. And I'm too lazy to convert, this is really, okay. Now, so the thing is that, where is that in terms of feet? So remember, what I did was when I added the member, okay, I started here, and then I went to there. So therefore, this is where the program considers that to be the I and the J, and therefore it starts, so therefore I can say 2 feet. If I had done it the other way around, then I would have to give the information from there. So that's why it's important to remember how you added your member. So what position is that? It's at 2 feet away from where I start, where I place the member. And what's the force? Of course, it's minus 2,000. And I press OK, and there you go. Now, you can always amplify your loads if you want to see them a little bit bigger, okay? And now I came out just to show you that that's placed at 2 feet away from where the member started. And now I'm going to double click on it again, and I'm going to go put the distributor load. Now, the distributor load, okay? The distributor load, again, okay, I'm going to need only one extra row in the spreadsheet. Now, what's the value here? Minus, okay, minus 400. So that's going to be minus 400. And where does the load start? Well, the load starts at 4 feet. And where does it end? It ends at 12 feet. And it does it by default, it gives you the value. And if you're happy with it, just press OK. And there you go. So now the load has been placed according to what you have here. And last but not least, okay, and that's why, even though this one has the same load, since it starts here and ends there, I can't pick them both at the same time. I have to do them individually. And now I double click on that one, do the distributor load. And of course here, all I have to do is put in the value, minus 400. And it's going to put a minus 400 there. It starts at 0, it goes all the way to 2. That's exactly where I want it to go. Press OK. And there's my load. Okay. So now I've done my model. I've loaded each member according to the load that I want to analyze. Of course, I got to tell the computer how to combine all these loads. Okay. And there are load combinations. Next year, when you're learning how to design in the reinforced concrete, I would teach you the 5 different load combinations that there is according to National Building Code, and that's where you would appreciate what they mean by load combination. This here is going to be a little bit boring because everything's going to be just 1, 1, 1 all the time. So don't worry about that. So here we go. So I've got my loads. Step number 3, how am I going to combine all these load cases? Well, I go back to loads. I go to load combination. I go to define my load combination. And here I need only one load combination. I'm going to call this one a live load. Okay, all my live loads are in there, my load factors. So here, what I'm going to do is I'm going to call up my live load. I'm not even going to include the self-weight of the beam for now, okay? Because this way we can check to see if the program is pretty good. I'm going to exclude the self-weight of the beam. If I wanted to put the self-weight of the beam, of course, I would add a second one, and I would put here dead, and it would include the self-weight of the beam, but I don't want to do that. I want to be able to check the results to get a good idea if the program is giving me something decent. So that's why I'll leave it out for now. Okay, so this is my load combinations. So now, well, you're ready to run some analysis, okay? If you get an error message, that means that the program is missing some kind of information. In order to complete the analysis, read the error message, and if you don't understand it, text me, or I'm sorry, email me, and I'll explain to you what the error message means. And if I cannot explain it through an email, we'll set up a Zoom meeting and we'll go through it, and I'll explain to you why you're getting that error message. So if you follow my steps, and if you're very, very careful and you don't skip a step, don't rush, trust me, when you get to the analysis, you'll avoid getting those error messages, okay? So now we are here and we are ready to run the analysis. Like I said, analysis, you can do it here. You want to run a static analysis because that's what you're doing. Okay, this thing can do, see, it can do moving loads, it can do dynamic analysis, it can analyze and design, so it can actually size this beam for you, okay, and so on and so on, okay. So it's a pretty powerful program. So here I like to use this little icon here, static analysis, okay, save project, yes, and of course, okay, analyze. And calculation is complete, you may consult your results. Close. So now you want to see the load that you want to see, that you want to analyze. So it's going to take all the loads that were under the load case live, and it's going to apply it to and give you the results of the analysis. And like I said, what I always like to do is I like to check always my reactions first. So I always go to, when I go see my results, I like to always look at my reactions first. And of course, here I know that, look, I'll put in Rx, but I'm not going to get a value of Rx because it's 0. Okay. And of course, bring it back to normal. Okay. Now, guys, this is, when you see 62,999.96, this is 6,300. Okay. And this is 2,900. You understand what I'm saying? This is the rounding off that the computer does. But if you were doing this manually, you would get, like, if I would be putting this value down, okay, as a result of my analysis, on my sheet of paper that I would record this, I would say, here my reaction is 6,300 pounds, and here my reaction is 2,900 pounds. That's what it is. You don't bring it to 2 decimal places, okay? That's the program that is rounding up, and it's like, I find that's ridiculous. So that's the real value. Now, if you want to check to see if the program makes sense, okay, what you're supposed to do, sum of f of y's and see if they add up to 0. So in other words, you take the 63 and the 29, which would give me a total of 6300 plus 2900, give me a total of 9,200. Minus 800 times 4 equals minus 2,000 equals minus 400 times 10 equals, and I get 0. So at least the sum of f of y's are correct, okay? And then, so this is perfect. Now, with these reactions, if I want to see if the program is totally correct, with these reactions, with all the loads I have here, in other words, here I have 6,300, and here I have 2,900, okay? And of course, what I'm going to do is I'm going to try to take, if I take moments anywhere along this beam. I don't care if I take them here. I don't care if I take them about that point, that point. Of course, what I would like to do is I would like to take them where I would have to do the least amount of calculations. Okay, so I would choose a point here, and I would take the sum of the moments about that point, and if it adds up to 0, the analysis of this program is correct. So guys, sum of f of x, sum of f of y, and sum of the moments about any point from which you get from the reaction will tell you if the $4,000 that you spent for the software has any value. And these 3 equations will tell you that, okay? So that's how you test any structural analysis program. You always check for equilibrium. Once you run the analysis, you put your reactions, and then you do the sum of f of x, sum of f of y, sum of the moments about any point, and if the 3 of them add up to 0, the program is worth what you paid for it, and it's got reasonable results. Just to let you know, that's how you test any software, and that's why these 3 equations are very, very good, very, very important. Okay, so there's my reactions so far. Like, I'm not going to waste the time to do that, but I'm pretty sure that it's going to work. Now, did you guys get the same values?
Yeah.
62,099.96 also? Or did you get like 6,300?
The exact same as you.
Okay, there you go. So it's like I said, this is rounding off, okay? So that's all it is. And okay, mind you, it would still add up to 0, but you understand? Okay, thank you. Clear the drawing. So now once I've seen my reactions, of course, I'd like to go see my shear. And so I'm going to go see my shear. I'm going to take this off. I don't need this anymore. I already put this on my piece of paper. So guys, on the assignment, what I'm going to ask you to do is you run the analysis, you take a sheet of paper. For problem number 1, you draw a line and you put the reactions you get for that, and then below it you put the shear diagram, below it you put the moment diagram for each problem, and that's what I want you to hand in. I don't want you to print this. I just want you to copy what you see here on a sheet of paper. For example, if this was the assignment, then I would expect you to do this. Like, in other words, you just draw a line for the beam. You give me the reaction here of 6,300. You give me the reaction here of 2,900, and then below it, you give me the shear diagram. Sorry, you give me the shear diagram, you understand? And what am I doing? The shear diagram, okay? And then you give me the moment diagram, as you see it on AD, with the values that you're going to see on the diagram. So that's what I want you to do. And this way I know that you're taking the information, you're putting down properly on the paper that you're going to be using to do your design. Now, as far as the moment diagram again, okay, so first we'll go to the shear. Now the shear is Vy. In other words, it's the shear with respect to the y-axis here. So I'm going to go here. I'm going to say apply. Okay. And of course, because I modified, remember I flipped my shear diagram. Now the shear diagram is in the same direction as we would normally see it. And does it make sense? Yes, it makes sense. Okay. Because here, if I take 800 multiplied by 4, I'm down to 3,200. Okay. Then, of course, if that wasn't rounded up, I would be up to 3,100 here. Okay. And then it's a constant. It's a constant. Like here, it looks like it's just the way that the program draws it, but it's constant. And then all of a sudden it drops down to 1,100 here. That's what this is, okay? And then after that, it goes over to 2,100, jumps up, and then it goes back down to 0. So there's your shear diagram, okay? And because what the program is doing is just like it's trying to attach these 2 points together. Now, if you would ask for 20 segments, of course, the diagram would be a little bit more representative, but when you're actually designing things, this is what's important. What's the maximum shear? And you get those values anyways. You really don't care what's happening in here. You just worry about the maximum shears. So that's your shear diagram. And after that,
I have a question.
Yes.
Yeah. So you say when we transcribe, like what's on the
screen.
What we see on ADA on the screen.
Yes.
The let's say the 3,200, it's minus 3,200.
Yeah, but
you
just write 3,200. You understand?
Okay. And how do you flip it?
Oh, you flip it, you're gonna go to your visual graphics, okay?
Yeah.
I'll take my time. Go to visual graphics, okay?
Colors.
Go to color, okay? And guys, remember when you're talking about your arrow sizes were too big and this and that, right? Well, if you wanna go, you go to, okay? And you go to, for example, your nodes, okay, and this is where you can modify all that stuff if you want. You know, it's up to you. You can even modify the color if you don't like the colors that ADA gives you, but that's okay. So let me just sorry. Okay, so you're going to go to excuse me. In your case, you want to modify the results, right? You want to write results of a member, and in this case, you want to read what we have is excuse me, the shear force, right?
Yeah.
And you want to modify the shear force with respect to the strong axis because you're putting the beam with the two flanges, one at the top, one at the bottom. So therefore, you would start with the strong axis. And just in your case, you have a positive value here, put a negative
Yeah.
value, and it's going to flip it.
Okay, so you just
You just change the amplitude factor from, and then the moment is the other way around. It's going to be, I think it's a negative value or it's a positive, and you just flip, change it around, and the program will flip the diagram the way that you would be normally seeing it from your physics class, what we did also a bit, you understand? So if I like to see it that way also, you understand? And it makes sense because according to our sign convention, if the beam is going down with respect to if the left side is going down with respect to the right side, that is going down, therefore it should be negative. You follow? Now, don't worry that this is what you really have to look at. You understand? Because this is 0 here, but there's really no negative or positive shear. There is negative and positive moments. In other words, it tells you which side the tension is on and all that. But as far as shear goes, it's just, okay, is that clearer?
yeah.
Okay. And like I said, when you draw it, guys, just draw it like this, and and then just give me the values, and that's it. That's all I want to see. And I want to be able to see that you guys are knowing how to extrapolate the information that you need to be able to actually design this beam if this was the results that you're going to be designing the beam for. You understand? For shear and for bending moment. So there's your bending moment, and like, I see this year after year. I mean, I don't know why people do this, and it's really, like what they do is I'm going to look at my moments and I'm going to look at my shear at the same time. They put both of them on and they look at them both at the same way. No, don't do that. Okay, like you're supposed to look at each one individually and get an appreciation of how the moments are, and so on. So do it individually. Okay, do it individually. I'm sorry. I want to see the bending moment now. The bending moment is mx. Okay, apply. Now, remember, this is the way that the bending moment, we would normally draw it. Now, if you remember, I don't know if you remember this, I think this was class number 4, okay? In class number 4, I told you what's considered to be a positive moment and a negative moment, right? A positive moment is when the tension's at the bottom, and a negative moment is when the tension's at the top, okay? So if you remember, excuse me. Okay, so this is your beam here, okay? And if you remember, according to, okay, if you remember, according to your, where's that? Okay, remember that this is a neutral axis, right? Okay, now, when the beam is simply supported, this is all in tension here, and this is all in compression here, okay? So what this is telling me right now, okay, is that here I have a positive value, okay? So that means the tension is at the bottom, right up to this point here. This is the point of inflection. And then the tension starts to being at the top. And then all of a sudden here, up to that point, that's the point of inflection. So the tension is all positive up here, positive down here. This is positive down here, all the way to this point of inflection here. This is all positive. And of course, then this is from here to here, it's all negative, okay? So that's what these things tell you. Now, why is that important? Because if this was a reinforced concrete beam, you always put the steel on the tension side. So if this was a reinforced concrete beam, what you would be doing is, let me change color. Okay, we have some blue. Oh, yeah. So if this was a reinforced concrete beam, okay, I would have to put the steel here, to make sure that I increase the tension, and then I would put the steel up here, and then I would put the steel down here, and then I would put the steel up here. So that's why it's important to know which is the tension side, especially in reinforced concrete beams. Okay, and that's what's nice about ADA. It tells you where the point of inflection is, where it goes from tension to compression, or where the tension flips from the bottom side to the top side, and so on and so on. And that's really nice. Okay. And like I said, if you ever want to see this, okay, and if you remember, according to our sign convention, okay, if you take a ruler and you twist it the way that this moment is twisting the end of this, right? I want you to try to picture this, is that if you take a ruler and you twist it up like this, the end of your ruler, you'll see that the tension is here. In other words, this is where the fibers are actually stretching, and then on top is where the fibers are actually pushing together, and that's what this is absolutely correct. In other words, ADA is doing the right thing. It's putting the tension, it's showing you that the tension is at the bottom and the compression is at the top, up to this point here, and that's what this is telling me. Okay. So guys, like I hope you're getting a little bit of more appreciation of what we mean by positive and negative. And it's just so that we know where the fibers are being pulled and where the fibers are being pushed together. Okay. And that's all it is. And of course, if you want to see the deflections, okay, if you want to see the deflections of this beam, okay, you go back. Let me clear the drawing because it's pretty messy. Clear all the drawings. I remove that, and I want to see deflection. Deflections about the strong axis, because it's bending about the strong axis. You place the beam with respect to the strong axis, apply, and there you go. So that tells you that this beam is going to be deflecting. Now this is in inches, so therefore it's going to be deflecting 0.05 inches right here, okay? And ultimately, if ever you want to see the results, and that's how I like to see them, what I can do is I can look at the results in table form. This is how I like to see my result. You understand? I like to go here and see my deflection, see how, you understand? And at the same time, and of course, I can ultimately print all this out and have all that printed so I can keep it as part of my, inside my file, so that if anybody asks me, what's the results of your analysis? And I would go back, instead of having to rerun the analysis, I'd have a hard copy of this. And I would definitely, if I was doing this for a project, once I've completely done my analysis and I've completely done my design, I need for 10 years, keep a record of what I've done. I would print this and keep it for 10 years in a file somewhere for that project. And that's it. So there, that's the one. And that's, you know, so here I took this example here because, like I said, the shape was in metric, the geometry was imperial, and so on. And I wanted to show you how easy it is that you could right away accommodate that in your project configuration. Does anybody have any questions on this? Now, I'm going to do one last example. Okay, I'm going to do one last example. And this time, I'm going to do one that I'm going to create a smooth pin in between the members. Okay. And then I'm going to do maybe one more after that. I don't think I'm going to do one. I'm just going to explain one thing for you. Okay. We'll bring up the assignment, and then I'll explain. I'll put the assignment up on the on the screen. Okay. And do you guys want to try this on your own, and then I'll do it, and we'll see how you're doing with the program, or do you want me to go through it? How do you guys want to handle this? You want to try this on your own, or do you want me to do it?
Maybe just like we're fine to do everything except, let's say, the spoot pin.
Yeah,
like
okay.
the spoot pin is
I know that's a
which axis to unlock.
Yeah, exactly. That's a whole new concept that you haven't been exposed to. Okay, so listen, I'll go through it, and then I think on the assignment you have to do one of these. I've given you one of these. As a matter of fact, you're going to have one of these on the next test, so you might as well get used to it. Now, okay, so what I'm going to do now, of course, I'm going to start a new file. Okay, let's start a new file. Everybody start a new file. Save what you've done so far, okay? And again, okay, now remember, when you first boot up ADA, everything is in metric, but if you're doing different files with ADA on the same, without rebooting it, you should always go back to file, go back to project configuration, and look at what the units you are working in. So here I'm working in metric, and my shapes are also in metric. So therefore I can just put metric, number one, that's good. And as far as the system of units I'm going to be working with is metric, that's good. So therefore metric and metric. Okay, so just to make sure, I don't know if you guys can see it, but there's a blue outline here. Everybody see that? Okay, there's a blue outline. So that means that you're working metric. And of course, this radio button is pretty obvious which units you're working in, because the radio button is either imperial or metric. And at the same time, like I said, remove these. Well, these you don't have to worry about. It's just these two you should be worrying about. Remove them all. And again, we're okay to go. So I like to do this at the very beginning. Now, like I said, before I even worry about ADA, okay, the first thing I do is I start by asking myself, well, I need to put a node here. I will definitely need a node here so that the member could interact with the reaction area. I will definitely need to put a node here because I need to create a smooth pin. I need to put a node there because I want the member to interact with the reaction area. I don't need anything here because it's just a load. I need to put a node here because I want the member to interact with the reaction area. And of course, I need to put a node here so I can define where this member is going to end. So this would be node number 1, number 2, number 3, number 4, number 5, number 6, and number 7. And then what I do is I come here and I say, this is 0, of course, 0, 0. This is 1, this is 2. So I'm sorry, this is 2. 2 plus 2, this is 4. 4 plus
Sorry.
2. Sorry?
Yeah, number 5. Where did you put it? It's just a
Oh, I'm sorry.
concentrated
No,
one
I
right
made
in
a
the middle.
no. I'm sorry. You don't have to put one. Let me erase that. You're right. Thank you for pointing that out. Okay. Why did I put one at number 5? Exactly. I'm glad you're starting to understand the program. You don't necessarily put a node where you have a load, but you'll have to do it for moments, and I'll explain that later. Okay. So you're absolutely right. So this is number 4, this is number 5, and this is number 6. Thank you for pointing that out. Like I said, this is 0, 0, 1, 0. This would be 2, 0. This would be 4, 0. This would be 6, 0. And this would be 7, 0. Now, what I like to do is always, make sure that when I add everything up, I know the overall length of my members. So 1, 2, 4, 5, 6, 7. I should end up with my last node being at 7 meters. So I know that I got the right length. That's number 1. Now, once I've done this on a piece of paper, I have the input that the program is going to require. And therefore, I am now going to start. Okay. And like I said, before I even start creating my structure, I'm going to tell the program, as I'm modeling my structure, please tell me what the length that I'm going to be receiving after I give you the input. Let me know the material that I've put in and let me know what shape I've assigned to my members. I like to do this right away. And at the same time, I like to get rid of this axis out of my face. So I like to remove the global axis system and I press apply. Okay, so now we're ready to go. So basically, we're going to go to structures again. Okay, we're going to go to nodes. And that's why 1, 2, 3, 4, 5, 6 nodes. 1, 2, 3, 4, 5, 6 nodes, right? Now, node number 1 starts at 0, 0. Node number 2 starts at 1 meter away. But node number 2 is going to be a support node. Node number 3 is going to start at 2 meters away. And it's going to be a normal node. Okay, even though it's a smooth pin. I'll show you how to create a smooth pin. Node number 4 is going to start at 4 meters away. And that's going to be a support. Then node number 5 is going to start at 6 meters away. And that's going to be a support. And node number 7 is going to be just a normal node, but it's going to be at 7 meters away. So because I'm not moving anywhere along the y-axis, this all stays to 0. So don't panic if you made a mistake. Like I said, you can come back and change anything you want. Okay, so by doing it on the paper first, you're going to minimize the mistakes that you could be making here. That's number 1. So press OK. So here we go. So here we got, so this is what we have, all right? So now I've got my nodes and I got my supports. I want to be able, okay, I want to be able for you guys to see all of them on, okay, so that's pretty much it, okay? So like I said, I've got my nodes, I've got my supports. In terms of modeling, I do it sequentially, that now I'm going to go to my supports and I'm going to model my supports. So I go back to structures, go to supports. Now, number 2, it is a roller. A roller means that it's free to move along the X, but it's not free to move along the Y. Okay, it's fixed along the Y, and it's also free to rotate about the Z axis. So it's free to rotate about the Z axis. So I've created now a roller as support number 2. Support number 4, and there you see the number 4. It is a pin, means that it cannot move in the X direction. It's fixed in the X direction. It cannot move in the Y direction. It's fixed in the Y direction, but yet it's free to rotate about the Z axis. So therefore, I'm going to free it about the Z axis. And number 3 is very similar to number 2. I'm sorry, node number 5, which I should say node number 5, very similar to node number 2, whereby it's free in the X, fixed in the Y, and free in the Z. So basically, MZ should always be free unless we have something fixed. We will be doing some analysis where it's all going to be fixed, so don't worry about that. And now that I have done that, just to double check, yeah, I only got a yellow arrow there. I got 2 yellow arrows there, and I only got 1 yellow, and then there's no more red dots. So that means I've freed the rotation, and I freed the displacement in the X, and I freed the displacement in the X. And don't worry about the red. Like I said, that's the 3-dimensional thing about the program. So now I've got my nodes, I've got my members, okay? I'm going to activate my members now. Okay, so make sure you activate your members. And once you've activated your members, you're going to add members, and therefore you're going to go, like I said, I like to go from left to right. So I have my I and my J node. I'm going to go from left to right. There's my first member, and it's exactly 1 meter. From there to there, another, oh, so far so good. Yeah, so far so good, 2 meters. This should also be 2 meters. That's good. And of course, 1 meter. So the member lengths are good. That means my nodes are placed properly. That reassures me, because guys, remember, with a computer program, garbage in, garbage out. It doesn't recognize that, so now that I've assigned the geometry, for my structure, I need to go inside the members. And of course, I'm going to get out of this command by hitting the escape button. Hit the escape button to escape out of the adding of a member. Now, since they are all the same shape and they're all the same grade, all the same material, I will simply draw a window and pick them all at the same time. Okay, so you draw a window, you pick them all at the same time, and then you right click, go to properties, and now you'll assign the properties. So we'll go to steel. And again, we have a wide flange section. That's the most typical shape that we use for steel beams. And this one's a very small one. It's only 150, so it's going to be all the way down here somewhere. There you go, 150. And it's a very light one. It's only 14, so there you go. It's right there. Okay, so W150 by 14. And that's what we're going to be, the shape that we're going to be assigning. Like I said before, if you want to see the sectional properties of this beam, you just click here. It gives you some geometric properties. In other words, it tells you what the B is, the D is, and so on. And this gives you the moment of inertia, the section modulus, the radius of gyration, the plastic modulus, and so on and so on. I mean, this is information that some people might need, okay? And this is exactly the same information that you would find in any steel book for this particular shape, okay? So here to tell you, this is the information regarding a welded Y flange. This is the information you get regarding a W, a HP, and an M, okay? And we will also be creating our own, okay? So I'll show you how you can create your own if you don't find it in here, and so on, okay? So you press OK for that. And of course, you press OK. So now Now, if you don't assign the material to you're going to get an error message if you run the analysis. Now, I could have done that purposely so that I could have got the error message, but I'm just letting you know that if you forget to assign the material with ADA, you will get an error message. You won't be able to run the analysis. Here again, I tell you, it's the American steel ASTM A992992. And of course, if you want to add, you might as well activate the dead load, because this way, if you want to add it in, it's already there. If you don't want, you just leave it out of your load combination. And if I press OK, well, it's a little bit hard to read, but okay, so there you go, W150, so beautiful. I know that I've assigned the right shape, the right material, and they are the right length. So now my model is complete because I went in a very systematic way, and therefore I don't need to know that information anymore. I double checked it, okay? Now, the only thing I like you to do, okay, is go to attributes. I want everybody to click on attributes. Go to view options, click on attributes, okay? And I want you to put a check mark on end condition. I'm going to repeat that. Okay, so you go to attributes and put a check mark on end conditions. Apply. Okay, now you don't see anything here, okay? But now I'm going to show you how to create the pin connection between the two members, okay? Right now, this member and this member, it's as if it's a continuous member. They're welded together. So I need to release the fixity between the two members. I need to create a pin. Now I can do two things. I'll do it to this member here. So I double click on this member, okay, and see where it says end condition. Fix. It's a continuous member. In other words, it's as if it's welded. It's one piece going right across. Okay, what I have is I have fixed on one end and I'm releasing it at the other end. This is my I, this is my J. So I'm going to press that. I'm going to press OK. And if I've done it correctly, what the program does, it draws a little circle saying you have released this end of the member to this one. Okay, and that's how you create a pin. Now, I could have done it to this member here. Okay, or I'm going to go back to fix. Or I could have done it to this member here, but the difference is that when I do it to this member here, and don't forget it's bending about the MX, not the MY, I'm going to release it on the other side. In other words, where my I is, press OK. And I'm doing exactly the same thing. What I don't want you guys to do, and I think is stupid, people release it on this side and on that side. That is redundant. This program will be able to correct that redundancy, but there are programs that if you do that, they will crash on you. So you don't have to release it on each side. As long as you release it on one side, it becomes a pin. You want me to repeat that? Okay, and that's how you create a pin with ADA. So in other words, what's going to happen here is that when we're going to look at the moment diagram, right at this point here, the moment should be 0. That's what the pin does. In other words, it does not restrict the the rotation of the beam, and therefore the moment is going to be 0 right at that pin. Okay. So now my model is complete. Okay. Is everybody good with this? Do you want me to go back on anything? Does everybody have exactly what I have? In other words, a circle. Okay. Like I hope you did on this side. It makes no difference. Okay. Like I said, the ones that did on this side, leave it on that side. The ones that I did on this side, leave it on that side. The ones that did on both sides, don't get into that habit, okay? And leave it like that, and I'll show you that at the end, we'll all get the same results, okay? So my model now is complete, okay? And this is, like I said, under the view option, under attributes, end condition, click that, okay? And that's where you'll be able to see that you've released and created a pin between the ends of those two members. Okay, if there's no questions, I'm going to go on. Or why don't you guys go on and apply the loads, and I'm going to apply the loads. We'll run our data analysis and see if we get the same results. How's that? So guys, go ahead, apply the loads. I mean, you see the loads there on the screen. So apply the loads, and so Save. Okay. There we go. How's everybody doing with the loads? Does anybody have any questions? Is everything good? So, is anybody having a problem putting in this triangular load on this member? Are we ready to run the analysis?
I'm ready.
Pardon?
I'm ready.
So you had no problem putting in this triangular load, right?
No.
Exactly. In other words, all you have to do is make, it starts at 2 and then just bring it to 0. Fantastic. And don't forget, did you do your load combinations?
Not yet.
Okay, so you wouldn't have been able to run your analysis. See, your model, your load cases, your load combinations, and then you're ready to analyze. So for example, if you were press FX, in other words, run the static analysis, you would have had an error message. Try it just for the hell of it. I'm going to do it right now because I haven't done the, see here, look. There is no load combination defined, so therefore the program doesn't know what you want me. It doesn't know what has to do with what you gave it in terms of information so far. Do you want to generate it? No, just say no. Okay. So therefore, that tells you right you forgot the load combination. So you're going to go define, and of course, I only have one load combination. I'm going to call it YZ. See, I can call it whatever I want, as long as I know what I'm doing. And here, this is my XYZ. And of course, the only load I want to put in there is my live load. I will not include the self weight of the beam because I want to be able to check the results quickly, and then I can go back and add it back. And now I'm ready to do the FX. Yes. Analyze, and we're complete. So now that it's all done, of course, this is what I want to see the results of. I just want to show you that the name you put for the load combination is for you to remember what you're doing. The program doesn't care if you call it, you know, whatever you want to call it. So now what we're going to do, of course, always in terms of results, always start with the reactions. Apply, and there you go. So this is in kilonewtons. That means I have 5 kilonewtons here, 18.33 kilonewtons there, and 1.17 kilonewtons here. And if I do the sum of f of y's, they should add up to 0. So therefore, what you would do for the assignment, you would draw a line, show where the reactions are, and give me the values. You understand? So those are the reactions. And then, of course, once I look at, I've noted my reactions. I would look at my shear forces to get my shear force diagram. And of course, I'm just going to make this a little bit bigger so you can appreciate, okay? So here's your shear diagram, okay? There you go, there you go, there you go, down, okay? Now here, of course, it drops because of that, that 10 kilonewton down to 0.17, up and back, and then, and because, I don't know if you guys remember, because I have a triangular load here on the shear diagram, this is parabolic, and it drew for you parabolically here, okay? So that's what it is. A triangular load on the shear diagram is parabolic, and on the moment diagram, it becomes cubic. You don't really see the difference because they're very similar curves, but this is parabolic on a shear and cubic on a moment diagram. So there's my shear diagram, and of course, ultimately, the moment diagram so that you can design it for bending, apply, and of course, perfect, okay? Perfect, perfect, perfect. And where the pin is, the moment is 0, and that's exactly it is. If I'm not mistaken, if you guys go back a couple lectures, we did this one manually, or you guys did it manually. We either did it in class or we did it as an assignment, and that's exactly the moment diagram you were supposed to be getting, you know. So here, it's exactly like we've been doing. In other words, where's that thing? Okay. Here is the distributed load, therefore it's parabolic. That's what it is. Here's the distributed load, therefore it's parabolic. Okay. Here it's a concentrated load, therefore it's linear. Okay. And of course, here what's happening. Okay. So then, well, here it's somewhat linear, you understand? Unfortunately. And then after that, here it becomes, believe it or not, it becomes cubic in here, okay? So there's my moment diagram. Did you guys get the same results or something different?
Same results.
Pardon?
Same results as you.
Same results, okay. So that's pretty good. That means we're either both right or we're both wrong. How's that?
I don't know.
I'm just saying. Okay, now guys, I'll tell you one thing I don't like about this program, okay? Let me just, I'm gonna clear everything here, okay? One thing I don't like about this program, okay, I'm gonna go to the mouse and I'm gonna have to, I'll be right back because I need to go and I need to open the assignment because I want to show you something on the assignment that we haven't done yet, but then if I don't show you, you guys won't know what to do with this, okay? And it's unfortunate, but this is one of the drawbacks I don't like about the program. I've used quite a few structural analysis programs in my career. This is a good one, but it's got us little, let's call it, things that I'm not too crazy about. So I just want to show you, hold on a second, Dawson, structural analysis, assignment. you guys, we're doing assignment number 7 this week, right? Is that it? I'm going to make sure I'm opening. Yeah, okay. So I'm going to stop sharing and I'm going to reshare so that you guys can, okay, stop sharing, share. Here's the assignment, okay? So basically what I want you to realize that this one you should be able to handle. This one you should be able to handle. Now this here, okay, it's because I took this out of a textbook and I didn't bother redrawing it, okay? So hold on a second, annotate. Okay, this is the way the textbook was showing that this is a moment. Okay, this is a moment. In other words, it's got 8.8 kilonewton meter. Now, in ADA, when you want to apply a moment as a force, you have to create a node. And you can only apply a moment at a node. You can't, you can apply it to the member, but ADA is going to put it right across the whole member. That's incorrect. So for this particular, even here, you're going to have to create a node here, so that at that node, you'll be able to apply this moment. That's all I'm saying, okay? And then, of course, this is going to be the one that we just did. So these are the 5 problems I'd like you to practice, okay? And of course, you have till the end of the day. I put the end of the day to submit your assignment. And I'd be more than happy to stay here until 3:45 if you want me to. Or if you guys want to go off and work on your own, just let me know what you want to do, okay? I just want you to remember that when you're modeling this one, put a node there, but also put a node here, okay? And that's only 2 moments. When it's concentrated loads, don't do it. It's not worth the time. So like here, I wouldn't put a node. It's just a concentrated load I can put on the member. But when it comes to moments, you have to add a node. And when I went to see the people at ADA, why do you do that? I mean, it's pretty, that's the way that the program was developed, blah, blah, blah. And they kept on giving me these poor excuses. But I found that was a really piss poor way of having to apply a moment to one of your a moment load to the thing. Okay? So there's the 5 problems. Like I said, you do each one, and then on a sheet of paper, you simply, show me the results, show me the reactions, and then show me the shear diagram, whatever shear diagram you have, and then just show me the moment diagram, problem number 1, problem number 2, And guys, when you do it, try to be consistent, like if you do it like so that the shear corresponds to the reactions and the moment corresponds to everything else, just so that you can get into the habit of doing it properly and it's easier to read. Okay, so I don't know if you guys have started on these assignments before the second lecture, but if you have, I mean.
I have a question.
Yeah, go ahead.
Yeah, so we see the size of the beam. So let's say W250 by 39.
Yes.
The steel, because it doesn't calculate unless you give material to the beam. So what is 350 MPa steel in the list?
Okay, so I'll show you where that is. Okay, fair enough.
Yeah.
Okay, so I'll show you where that is. So in other words, excuse me. Okay, so because when I gave this assignment way back when, they were still producing Canadian steel, and I was using the Canadian steel. Okay, but then I'll show you where that is. Okay, clear all. I'm gonna stop sharing. I'm gonna go back to share. I'm gonna go back to okay, so when you're ready to assign the material for these assignments, okay, and for example here, I'm going to first, see, now, these things are in the way, sorry about that. Okay, so basically, now I'm going to go back and modify this one. So if I want to modify this one, I have to make sure I activate the structures mode, otherwise I won't be able to do anything, okay? Then after that, of course, I'm going to pick members, okay? And of course, I want to pick all the members, okay? I'm going to right click, go to properties. And when it comes to materials, okay, go to steel, go to G40, okay. The 350W is right here. See the 350? That's 350 megapascals. That's where it is.
And
okay.
the one down.
And this is also the 350. I want you to take the 350W. Pick this one right there. Okay. That used to be the right steel that when these shapes were being produced in Canada, that was a steel that the Canadian mills were actually producing them to. So use G40.21M-3W. The W stands for weldable steel. The 350 stands for 350 megapascals for the yield strength of the steel.
Okay, and another question.
Yeah.
The material, this is just for ADA to calculate it. Because unless, like, the only thing that's going to change is the deflection, right?
No, no. What happens is that, okay, so now that you'll understand how ADA works, okay? Okay. What happens is that these programs, okay, actually calculate displacements, okay? And based on those displacements, they're able to calculate the forces in the member. And in order to calculate those displacements, it needs two pieces of information. One is the moment of inertia, okay? And the second one is Young's modulus, the E value. Do you follow?
Yeah.
And therefore, when you specify that value, it goes into his database and it takes the E value for that material to do its calculations.
Okay.
I know. Like right now, I'm talking right over your head. Okay, but if you really want to understand how these programs work, they use the stiffness of the member to calculate the displacements, and once it's able to calculate the displacements from those displacements, it can calculate the force in each member.
Okay, but the thing is, I did try it out, like changing like 350 for another 350, and it didn't change any of the shear diagram, moment, or reaction.
No, because the Young's modulus is the same for all the steels.
Okay.
You see what I'm saying? See, when it comes to structural steel, whether it's 350 or A992, or the E is the same, it's assumed to be the same value. You know where it make a difference? If you ask for the stresses, okay, let me show you, okay? We ran the analysis here, right? Now, if you look at results, okay, and load combination, I haven't run the, I have to rerun the analysis because I changed the material. Like, so now I put it to 350, okay? Now, where it's going to make a big difference is that, excuse me, when I'm going to rerun the analysis. Now, this is like, keep yours at the American one. Okay, run your analysis at the American one, that the A992, that's what you have on this one, right? On this example?
Yeah.
Okay, so keep your results, okay? And I'm going to run this one with the 350, the G40.21 350W, and I'll show you where the difference is, okay? So now I'm going to run the analysis. I have to rerun the analysis because I modified, okay? Analyze. Now, if we're looking at the forces, we have exactly the same thing.
Yeah.
You agree?
Yeah.
No difference, right? We have exactly, because the modulus of city and the moment of inertia are the same for the different materials, okay? Now, where the difference would be is that if I want to know stresses and not forces, when I go to results and I go to load combinations and I go to member internal stresses, okay? If you look at my stresses and if you look at your stresses, they're going to be slightly different.
Okay.
Try it. Open yours. Go run your analysis. Close. Okay. I'm going to close this. You've already ran your analysis, right?
Yeah, but I did it by accident.
No, I'm just saying.
I changed the material too.
You changed it. Okay. I wanted you to leave the same material. I want you to see where the difference would occur. You understand? So because you're using
would occur between points 3 and the one member that you modified.
Well, what I'm saying is that, for example, I would say, let's pick the same member. So, for example, I would pick this member here. You understand? And all of a sudden, I would say, go to results. And if I wanted to see the stresses now, not the forces in the member, in other words, I want to see member stresses, internal stresses, right? This is where you would see the difference in the values that you see in this table. It wouldn't be much because one's 350, the other one's 344.5.
Okay.
You follow what I'm saying?
Yeah.
So this is where you might see a slight difference in the stresses.
All right.
Because your Fy is slightly different. Okay.
Yep.
So like, and I'm glad you asked me that question because, you understand? So as far as the analysis goes for forces, exactly the same value, but, and then at the same time, if you'd ask the program to design, it would limit itself on that strength of steel to be able to select the member. That's the other difference. Okay.
Okay.
So I'm glad you asked me the question, but now just to give you a little bit of appreciation. But when I was telling you that I'd be talking over your head, I mean, when I took this way back when in school, okay, believe it or not, we were actually had to build the program to do the analysis. We had to build the matrix and this and that and know how to build a matrix, where to put, you understand? So
Yeah.
so my understanding of this program is like the nuts and bolts of it, not just the application. You see?
Yeah.
Okay. So that's it, guys. I have nothing else to say. And like I said, when it comes to those moment diagrams, don't forget to, add a node where the moment is so that you can apply the force. And remember, counterclockwise, positive value for ADA, clockwise, negative value for the moment, okay? And right now, I'm gonna stop sharing. I'm gonna put the record on pause.